So nobody, in case you haven't been there the past couple of days, nobody needs to be worried about lunch because there's a box lunch for everybody, and that lunch is cold anyway. So don't worry about it. Your lunch is going to be just as good 10 minutes later. So we're 10 minutes behind, which is not so bad. So Jacob Leyden is going to tell us about Arrp next. Go ahead.
Thank you.
I turned this thing off. This is so useful.
Yeah, it's a little blinding. Ooh. Is it set to 20 minutes?
It's set to 25 minutes.
Oh, great. Okay.
30 minutes. You want 2:30?
Well, and then it's set to 30 minutes, so shortly before that, we should post for questions. Okay, go ahead. Anyway.
So I'll talk about Arrp, a language that I designed to experiment with syntax, semantics, and compilation techniques for signal processing. So Arrp was primarily motivated by the requirements of audio synthesis and analysis, but it could be useful for a broader set of stream processing, basically everything that can be represented as a synchronous data flow, for example, video, sensor arrays, possibly even communication and multimedia compression protocols. So to support these domains well, we want to have multidimensional signals and multi-rate signal processing. And that's because that allows us to naturally represent things like bundles of audio channels or video or data from sensor arrays or different signal domains like time and frequency domains. This can nicely be represented with multidimensional arrays and giving some semantics to different dimensions. And similar to languages like Faust, Chronos in the audio domain and stream it in the more general stream processing domain, Arrp also strives to raise the bar on code reusability. So what we would like to have is we'd like to have to easily compose smaller signal processors into larger signal processors, and we'd like to do that without any performance overhead. So Arrp also wants to support real-time execution, so things like static resource usage, no dynamic memory allocation, and it also wants to have as little overhead as possible, and so it can be also used for high-performance processing in non-real time. That's also one of the goals. So let's look at some solutions that Arrp employs towards these goals. The first thing, especially in Arrp, is that signals are represented simply as multidimensional arrays with one infinite dimension. And what does that mean? That means that we can use the usual array indexing notation to index the infinite time dimension of arrays. And what that gives us is syntax that is very similar to the common mathematical notation in digital signal processing. So we can look at a mathematical formula and it almost directly translates to a program. Arrp also has array semantics inspired by languages used in scientific computing like MATLAB Octave and the NumPy Python library. And by that I mean pointwise operations on arrays, broadcasting, things like that. And what Arrp does is combines that with the functional paradigm, so polymorphic and higher order functions and type inference. And these things together will provide significantly improve code reusability, as I will show. Now, to achieve good performance, what Arrp does is what the Arrp compiler does is uses polyhedral modeling and optimization. And this is a technique that is used mainly for optimization of computations on large arrays. And it goes all the way back to 1967. But there's a lot of research ongoing right now because polyhedral modeling exposes parallelism in programs, and with increasing potential to use parallelism, that's becoming more and more interesting. So Arrp uses algorithms particularly a polyhedral scheduling algorithm was developed in 2008, and it is implemented in the integer set library that Arrp uses. And I'm going to give you a brief overview of how this technique is used. There's more information in the paper, and even more on that part is planned for a future publication. And if you want, I can also give you more details after this talk. So let's look at what it means for signals to be represented simply as arrays. So let's look at the first example here, where the sine wave function defines, well, a sine wave, and that is defined simply as an array, which in turn is treated just as a function from integer indices to some value. And here, t implicitly goes from 0 up to infinity. In the second example, we are differentiating the input signal x, and each value of the resulting array uses two values from the input signal, and it achieves that simply by using the array indexing notation. And in the third example, you can see how multi-rate signal processing can be achieved by simple arithmetic on indices. So the downsample function downsamples the input signal x by a factor of k, which means that every of the output samples at time t is equal to the input sample at time k times t. Recursive arrays can be defined easily in Arrp, either by reusing a name in its own definition, or just using the this keyword, which refers to the nearest enclosing array definition. And you can see that in Arrp, you can define arrays in parts with the syntax that is very similar to Haskell's patterns and guards. So in this example, the low-pass recursive filter is defined in two parts, one for the index 0 and one for all other indices. Now, how about multidimensional signals? Well, in the first example, you see A and B, and each of these arrays represents 5 harmonics. So this is a bundle of 5 signals where each signal is a sine wave at a multiple of some multiple of 1 hertz. But they are represented in slightly different ways. So in Arrp, only one dimension of an array can be infinite, but it can be any dimension. So A has the first dimension of size 5 and the second dimension infinite, and it can be thought of as an array of signals. B, on the other hand, has the first dimension infinite and the second dimension 5, so you could think of it as a signal with array elements. So all these things are really easily represented in Arrp. And the definition of these arrays does not actually depend much about how we treat dimensions. In the example number 2, you can see how we could now differentiate, so implement the same differentiation algorithm that we had before, but either over time or over channels, if we call the individual harmonics channels of A. But what we would really like to do is we'd like to reuse the functions sine wave and D that we have defined before as single-dimensional arrays, and we would like to reuse them to define these same two-dimensional arrays. And Arrp has a couple of tricks that will help us with that. So firstly, because arrays are just functions from indices to some value type, we can consider array currying just like functional currying. So an array can be seen, a multidimensional array can be seen as an array of arrays. So in this sense, we can create the same two-dimensional arrays, as you can see in the example number 1, by nesting array definitions. Due to array currying, we can also partially apply arrays, which I also call partial indexing. So if we partially index A, we get a whole signal, one of the harmonics. If we partially signal B, we get 5 samples, one from each of the harmonics. Now, what this allows us is to define the same A by using the sine wave function, like you see in example 1 here, or the same differentiation of all the harmonics of A over time, as you can see in example 2, by using the function D. Arrp also borrows the idea of pointwise operations and broadcasting from systems like Octave and NumPy. So, for example, in the example number 1, what we are doing is we are now differentiating over channels of A, but we are doing that by simply applying the function D to the whole array A. Now, because A is two-dimensional, inside the definition of D, xn+1 and xn each mean an entire signal. So the subtraction is applied pointwise to all elements of these signals. And we end up again with DCA being a two-dimensional array. Now, in the example B, in the second example, we see how B is defined by simply applying the function sine wave, but what we give it as the argument is actually an array of 5 numbers. And this is first divided by a scalar standing for sampling rate. And what happens here is so-called broadcasting. So we have values of different number of dimensions. In this case, one-dimensional array and a scalar, which can be thought of as a zero-dimensional array, which means that the same value of SR will be used to divide each element of that array, and that's called broadcasting. And now the result is an array of 5 frequencies, and that is passed on to sine wave. And inside sine wave, again, all the primitive operations are going to be applied pointwise after broadcasting. Now, the example number 1 here is repeated from the previous slide. You may have noticed that we are applying D over A, so it will differentiate over channels, which is a finite dimension of A. But how is that possible? Because in the definition of D, we did not specify any upper bound on N, and so it appears to be infinite. Well, this is possible because Arrp does automatic array bounds inference, and it does that by looking at how the index N is used when indexing the array X. So, because the largest indexing expression here is n+1, and the first dimension of X is 5, N must be less than 4. And so the result is just the maximum array we can get using these indexing expressions. Right? And likewise, in the second example, we do differentiation of A over time. And here, simply I is inferred to be bound by 5 on top, because the size of A in the first dimension is 5. So what you can see is that pointwise operations, broadcasting, array bounds inference, and array nesting increase code reuse, because we can use the same functions that were defined as single-dimensional arrays to define or process multidimensional arrays and signals. So that is combined in Arrp with typical features in functional languages like polymorphic and high-order functions, type inference, partial function application, function composition. And all this allows us to define and use the typical combinators. So here we have map, scan, and fold. Now, recursive function application is not yet supported in Arrp, and I will tell you later why not. But some uses of recursive functions can be replaced using recursive arrays, like in the definition of fold here, which is defined as the last element of scan, which is a recursive array. In Arrp, we can also define some abstractions which are otherwise built-in primitive operations and many other languages for signal processing, like Faust or Chronos, like delay, which delays a signal by one sample by prefixing some concrete value in front. Or win here, which creates a two-dimensional array which represents a sequence of sliding windows over the input signal. So with this, we can implement our low-pass recursive filter as using a delayed version of itself. Or we could implement a general finite impulse response filter as a map over windows of the input signal. So what does Arrp compiler do to achieve high performance? So let's look at what polyhedral modeling and scheduling means. We will use this example that you see in the box labeled 1 on the top left corner. And what this example does is y is defined as the difference of each consecutive non-overlapping pairs of x. Now, in the polyhedral model, programs are represented as a set of statements which manipulate arrays, imperative statements. So, like you see in the box number 2. So in order to use that, what we have to do is we first have to reduce functional language Arrp into such a set of imperative statements. And the way we do that is we do all beta reductions in the compiler. And that's the reason why, at present, functional recursion is not supported yet, simply for the reason that to ensure that this beta reduction terminates. In the future, I'd really like to see something more fancy that will actually allow some functional recursion. In the diagram before, under the box number 2, the data dependencies between x and y are depicted, and lines represent data dependencies between elements. Now, what polyhedral scheduling does is to map the individual spaces of these statements into one common multidimensional space where all the data dependencies are positive, which means all the producers of data are scheduled before consumers. But it also uses linear optimization techniques to minimize those dependence distances, which is called the data reuse distance. And after we have a schedule like that, what we can do is we can generate, again, imperative code that will visit all these points of a schedule and execute iterations of statements that are scheduled at those points. But the code that you see resulting from this procedure in the box number 3 is actually not feasible for execution in case of infinite streams. And that's something that's not yet well supported in polyhedral tools because they are mostly used for finite arrays. And firstly, of course, we don't want unbounded memory usage, so we cannot really represent infinite arrays in memory. So this is one reason. Another reason is that the index u that represents the time dimension would necessarily overflow as it goes up towards infinity. Right? So the unique thing that the Arrp compiler does here is to look at the schedule and find a period, extract this period, and generate a function which is supposed to be then infinitely repeated by the environment. And what happens to infinite arrays is they are turned into finite buffers. Right? And this is the kind of code that you see in the box number 4. But polyhedral scheduling can do more than just allow us to generate code that executes our program correctly. It also allows to expose parallelism that would otherwise not be found. For example, let's look at this definition of the finite impulse response filter. The definition of the FIR function is actually the same as you have seen before. The only addition here is that we have 2 inputs, one input for x, which is our input signal, the other input for coefficients of the filter. And essentially what this boils down to in the polyhedral model is these three statements. One statement X that represents the input, one statement that multiplies windows of the input with coefficients, and another statement B which sums these windows together. And here in the diagram, time goes from left to right, and elements of windows appear vertically. Now, one thing I want to bring your attention to is how every input element is used in multiple windows. Now, what polyhedral scheduling does is it skews the schedule, the execution of iterations with statements, so that all iterations that depend on the same input value get executed right one after another. Now, if we remove the, and here in the offset within a cell is represented as represents the third dimension of the schedule. Okay, so if we take away the input iterations here, which are colored in orange, we get what you see on the right, and you see that there is no data dependencies between the cells in the vertical direction, so all of those can be executed in parallel. So what we get here is we get parallelism in a finite impulse response filter without increasing input-output latency, whereas normally we would only have a what is called pipeline parallelism, which increases input-output latency. Oh, and you can also see that such skewed schedules are actually not periodic right from the start. So the part before the onset of the first period is extracted separately, and we call it prelude, and it has to be executed once before we can start infinitely repeating the period. So I'll just do a quick dive into the C++ code that our compiler generates. We have a class program. We have two functions for prelude and period. And the class program has a template parameter IO, and an instance of this IO is supposed to be provided by the execution environment. And whenever input data is required or some output data is ready, functions are called on this instance of IO to perform the input and output. So this way we can delegate input and output to whoever wants to use this class. And we could use this class to generate, for example, VST plugins or LV2 plugins, or embed this into any other system for signal processing. And you can see how arrays are, memory used for arrays is minimized down to finite buffers, and some of those buffers, some data that does not even have to be reused across repetitions of the period, can simply be statically allocated at the beginning of the period right on the stack. And then the indices for these buffers sometimes have to be offset at every execution of the period, and we achieve that using a so-called buffer phase, which is here B_PH, and that buffer's phase itself is incremented every period and wrapped around. Well, we did some experimental evaluation of Arrp, and we decided to compare it to handwritten C++ because C++ is still, and C++ are still the most widely used languages for high-performance signal processing nowadays, and Arrp attempts to replace them in some use cases. So we evaluated on three programs. The SYNT program is a 10-voice synthesizer, where each voice consists of an oscillator and two recursive filters in series. The EQ example is a 10-channel equalizer, where each channel uses a 64th order finite impulse response filter, and AC is short-term autocorrelation performed every 512 samples. So what you see is a significant speed up in Arrp in the SYNT and AC examples. And if we look at the generated code, the actual assembly, we see that in the case of SYNT, this is because of much simplified buffer buffer accesses, there's much fewer instructions executed that wrap the indices in buffers and so on. In the AC example, this is due to increased opportunities for vectorization that the C++ compiler gets. And we can attribute both to polyhedral scheduling. We also evaluated the amount of memory that is used for buffers, and in the case of Sint, you can see that Arrp uses a bit more buffers, and we can also attribute that to the different schedules. So in future, we could look at how to balance performance versus memory usage. And finally, you can see that Arrp uses much fewer lines of code compared to C++, which would be expected of a functional language. Finally, I'm just going to go quickly over some ideas for future work. So what we'd like to see is algebraic data types. We'd also like to see recursive functions. And I have some ideas how functions that are decidably terminate could be just reduced by the compiler. And those that decidably do not terminate could be converted into infinite arrays. But there's work to be done there. We'd like to have foreign function calls, and then we'd like to do actual multi-threading and generating GPU code, and it would be great to compare that to Faust, Kronos, and Streamit, the way they do it, and how polyhedral modeling compares to those approaches. And finally, I think there are some principles that could be reused and applied possibly in other languages, and I would really like to hear suggestions from you how, for example, some of that syntax, some of that semantics or polyhedral scheduling could be applied to other more established functional languages. And here's where you can get more information. Yeah. Thank you.
Time for about one question, I think.
Are you guaranteed that the backward data dependencies will only lead to finite?
Sorry, can you repeat that?
So you generate your graph that shows you like this now depends on the value of that 7 steps ago. Is there guaranteed to always be? Is there always going to be an upper bound for any program?
No, not. So it's either going to be infinite because the output signal is going to depend, say, on always a constant time of another signal. That in that case we can just buffer this one single number, right? In the other case, if you just look at the signals, the time, yeah, this can be unbounded, but polyhedral scheduling will schedule the other signal so that the distance is actually always constant over time. And that's always possible because polyhedral modeling limits the indexing to affine expressions, and it uses linear programming and affine functions to do the mapping, so it's always possible to do that.
Would that still be possible if you add in recursion?
If you had, sorry?
If you add in recursion, like if you add in general recursion, would it always still be possible to do that?
Yeah, I don't see why recursion would change this fact. Yeah, maybe we could talk later about why I think this would affect things. But we are not necessarily limited to affine indexing. One thing that we can do is indexing can be non-affine. For example, you can implement a wavetable oscillator where over time you're actually like dynamically depending on the value of, say, frequency, looking up data in a finite array. And that lookup is going to be non-affine. It's going to be value dependent. And what you can do in the polyhedral model is you can just over-approximate. You can say, OK, I'm just going to assume that every iteration of my output signal depends on all of this array, right? But of course, you can find a valid schedule for such a program only if this other array is finite. If it's not, then the compiler will tell you, oops, I cannot schedule that. Right? It doesn't compile because it doesn't make sense, right?
Thank you, Jake.